All right, so today we're going to be talking about some different factoring techniques. We'll kind of be reviewing some of those factoring techniques here. Remember, when we are factoring, we're talking about rewriting an expression as a product. So if we ever want to check our work, we're going to be checking it using multiplication. Some things are not going to be able to be factored. If it's not possible to factor, we say that it's prime, just like a number that only has the factors of itself and one, like 7 or 13. The first type of factoring is the type that we should always check for. It's called greatest common factor, and that means we're looking at all of the terms of a problem and determining if there's anything in common to each of the terms that could be factored out as that GCF. Think of this like undoing distribution. So I'm going to do number 5 with you here. I'm going to look first at the coefficients and consider if there's any common factors. Obviously, 1 is a common factor to both, but 5 is also a common factor since 5 can go into itself, and 5 can also divide evenly into 25. So I'm going to make a note of that out front of my parentheses that I'm going to be writing. You can also think of dividing both of the terms by whatever we decide the GCF to be. So I'll mark 5 as what I'm going to divide by here as well. Then I look at the variables. For x squared and x, those both have a common factor of x. So I'm going to take that out as well, or divide that out. So I'll mark that up front. So this is going to be the part that's my GCF. I'm going to divide 5x squared by 5x, which would leave me with just x. Another way you can think about that is think 5x times what would get me back to 5x squared, and fill in that what here in that first term. And then similarly, I'm going to divide 25 by 5, x by x. That's going to leave me with just minus 5. And that's just from the 25 and 5. And then again, I can check this by distributing or by multiplying. So 5x times x would get me back to 5x squared. 5x times negative 5 would get me back to negative 25x. So that's going to be the factored form of this original expression. Moving on to a second type, it's called difference of two squares. When we say difference, we should be thinking subtraction there. So you're going to be noticing you have this type when you have subtraction falling between two perfect squares, two terms that are perfect squares. Another way to think about this is as if this is a trinomial with a missing middle term. We'll do some more with trinomials here in a moment, but it's as though you've got an x squared term, you're missing that x term, and then you have your constant at the end. So I'll show you kind of how that impacts our factoring. So I'm going to set this up with two sets of parentheses just as though I were factoring a trinomial. I'm going to think, okay, I need to factor x squared. I'm going to factor that into x and x, since those would multiply together to get me x squared. And then if you treat this like it's that constant in your trinomial, think about your factors that multiply to get you 25. So that would be 1 and 25, or 5 and 5. The thing about the difference of two squares pattern is you're always going to be choosing that pair that matches, and here's why. If you think about it, if I want to multiply to get a negative 25, but I don't want there to be this middle term, that means that my inside and outside pair needed to cancel each other out in order for that middle term to disappear. So in order for us to be able to achieve that, I need to make one of these 5's positive and one of these 5's negative. So that way, when I multiply my inside pair, I get a positive 5x. I multiply my outside pair, I get a negative 5x. Those would cancel like they're supposed to when I check it. And then positive 5, negative 5 would multiply to give me the negative 25 that I need. So things to watch out for in this section: if you don't have a difference, that's going to impact whether or not you're able to factor it. And if you didn't have a perfect square here, or here for that matter, in one of your terms, that would impact whether you are able to factor it as well. All right, moving on to our trinomials here on the back. Our trinomials, you're going to be setting up just like how we started our difference of two squares factoring. So you're going to be looking at two sets of parentheses. I'll do number 19 here with you.
So again, you're going to be thinking x squared, what would multiply to get you that? That would be x and x. Look at your last term, your constant there, and think about your factors of that term. So my only factors of 3 would be 1 and 3. I need to be able to multiply to get negative 3, but then when I check my inside and outside pair, those pairs of terms there need to be able to add to get me 2x. Add or subtract, I should technically say. And a little hint, if you look at that symbol, if that's a subtraction symbol there, that means you need a difference that's going to become that middle term. If this were addition, like here, you're going to need these two terms to add to that middle term. So that's just a little trick to kind of help give you a nudge in the right direction. So I'm going to place 1 and 3, since that's my only pair, into my parentheses. Sometimes we'll have multiple pairs. We'll have to test multiple pairs out here. Now, if I want these pairs, when I've multiplied my inside and outside, to add to 2x, I need to make sure that I have a positive 3x and a negative 1x. And if I check that, that would add up to positive 2x. My middle term matches up. If I check my last pair here, negative 1 times positive 3, it does get me negative 3. So that would work out as making sure I've been able to multiply this back together to the original. So this would be your factored form for that problem now. All right, I'm going to pause here for just a moment and switch to a second video where I'll do a guess and check problem, but that takes you through at least 3 of the first different types.